Very nice to be back in Hyderabad, where I spent a large part of my professional career, almost 28 years. And I have never had the occasion to speak in this auditorium, which came up in the last 4 or 5 years. So lovely to be back in Hyderabad. And my thanks to the Academy to give me an opportunity to talk about this contributions of Professor Sudarshan, with which I have had some overlap in my professional career. So let me begin with some remarks on a justification for being here. I have neither been a student nor a postdoc with Professor Sudarshan, nor have I written any papers with him. However, my thesis work on personal representation techniques for stochastic description of chemical kinetics was largely inspired by his diagonal representation, about which I think Simon will talk about that a little later. At this stage in my career, I had not met Professor Sudarshan, but my supervisor, Crispin Gardner, had. He was a postdoc at Syracuse with him after completing his PhD with Dalits in Oxford. And I happened to ask him the question as to, because he had been to many places like Oxford, Cambridge, and so on. So I happened to ask him, who was the most impressive person that you've come across so far in your life? Without batting an eyelid, he said, ECG Sudarshan. He said the first day he walked into his office in Syracuse, and he had the feeling that he was in the presence of somebody who knew everything. Years later, when I joined the Institute of Mathematical Sciences as an assistant professor, and when I met him for the first time, I felt that whatever the description, how accurate the description which Crispin gave of Professor ECG Sudarshan was, how accurate it was. In fact, I mean, his very presence, his very wry sense of humor, his a glint in his eyes really unnerved you. And I mean, I'm sure that others who have known him for a longer period would vouch for the accuracy of this description. Now, recently, purely by accident, I found a photograph almost taken 20 years ago at a conference in the S.N. Bose Center, and this is perhaps the only picture I have with Professor Sudarshan. It also has Professor C.K. Majumdar, who was a person whom I've also greatly admired for his no-nonsense approach to physics. No hand-waving approach to physics. So this is a very nice picture of ECG and Chanchan Majumdar, and I had the honor of being with these two great gentlemen. Now, I would like to sort of summarize some of his major contributions to open system dynamics, something which he started much ahead of its times, and in order to make clear what exactly his contributions were, some amount of technical details, like what is meant by state of a quantum system, will be essential. So with due apologies to those who are not who are experts in these areas, I will begin with small introduction to just a statement as to what it is, to what is meant by specification of a state in quantum mechanics. So in quantum description of any system precedes with associating a Hilbert space with it, which is just a vector space. Elements of this vector space are conventionally represented by ket vectors like this. The scalar product between the vectors is denoted in this manner. Then we consider the unit ball in this Hilbert space, namely the set of all states which are normalized to unity, that is given here. Physical states of a quantum system are in one-to-one correspondence with positive operators on this Hilbert space, and these are referred to as a density operator. So physical states of a quantum system do not relate directly with the elements of the Hilbert space, but to an operator on this Hilbert space, which has the properties of being, it's a, by construction, a positive operator with trace 1. And what is meant by a positive operator is given here. Its expectation value in any state must be a positive or a zero number for all elements in the Hilbert space. Physical states, again, in order to accommodate all possible physical states that one would have to deal with in a given situation, can be divided into two categories. These are called pure states if rho is a projection operator captured by this property here, and they are called mixed if this is not so. Now, rho is a pure state if it's a projection operator. Rho is called a mixed state if it is a what is called a convex combination of pure states. That means pure states weighted by a probability distribution. So mixed states can be viewed as an ensemble of pure states weighted by a probability distribution Pi. Now we come to having defined what is meant by a state in quantum mechanics. Next step is to define what is meant by evolution. What is the equation that governs evolution of a quantum state? And this is the Schrodinger equation written down in the for the density operators, and H is called is the system Hamiltonian. Those of you who are not familiar with it may not worry too much about these details, but I think I would be able to convey to you what was Sudarshan's achievement in this present context. The Schrodinger equation given here, so evolution of a closed quantum system is described by the Schrodinger equation written in this form, and this can be formally integrated to yield the solution of this differential equation, which can be written as rho of t, a unitary operator acting on the initial state times the adjoint of the unitary operator, which is governed by the system Hamiltonian. Schrodinger evolution can be viewed as a map taking density operators to density operators. I mean, this is what you would expect. I mean, after all, once you have defined what is a state, evolution would mean some process which takes or evolves a state into a state. Now, because of the unitary nature of the evolution, which preserves the eigenvalues of the density matrix, you can see that its unitary nature has a consequence that it will take pure states to pure states, mixed states to mixed states, and therefore, in some sense, this evolution will not allow the possibility of taking a pure state into a mixed state. It will not be possible to describe things like a relaxation phenomena in quantum mechanics. You cannot be done with the Schrodinger equation as given here. So now ECG, in fact, in this paper in 1961, asked this question: what is the structure of the most general evolution which takes density operators to density operators? After all, once we have said that this is what is meant by a state, a natural question to ask would be, what is the most general possibility that evolves a state vector into a state vector? This question was raised and answered in a paper in 1961 by ECG Sudarshan, PM Matthews, and J. Rao. And this was the title of the paper was Stochastic Dynamics of Quantum Mechanical Systems. And the answer to this question was found, and the answer to that question was that a transformation, the most general transformation which takes a positive operator or a state to a state is given, has to be of this form, where these operators W alphas, in order to preserve the state, preserve the trace of of the density operator must satisfy this condition. So this was the most general structure that is possible for this evolution of a density operator, and this question was, remember, was raised in 1961, and I think in what I have to say a little later, you would see that how this work was far ahead of its times. Now, some remarks. Schrodinger evolution arises as a special case when there is a single term in this summation. Though the Sudarshan-Matthews-Rao derivation contained a gap, the result in itself had far-reaching consequences. It yields the structure of evolution of open quantum systems. Remember that closed systems are described, the evolution is governed by the Schrodinger equation, which is a unitary evolution. The structure which was given by SMR allows for the possibility of going beyond beyond unitary evolution and gives you precisely what the structure of the evolution should be. And it yields the structure of evolution of open quantum systems, dynamics of systems, of a system S regarded as a subsystem of a larger system, S plus R, and R is usually referred to as the rest or the reservoir, and provides a framework for discussing relaxation phenomena in quantum systems. Just to remind you, the earlier framework evolved pure states to pure states, mixed states to mixed states, but it would not allow for the possibility of a pure state evolving to a thermal state, for instance, something which you would require in quantum statistical mechanics. The SMR evolution, viewed as a map taking density operators to density operators, is commonly referred to as the Krauss representation, and the operators W alpha therein as Krauss operators, though SMR work preceded that of Krauss by almost 10 years. So here again you have a similar situation, similar to what one has in the context of diagonal representation, where the diagonal representation discovered by Sudarshan came to be known as Glauber P representation. Similarly, this work of Sudarshan with Matthews and Rao came to be known as Krauss representation. And in spite of the fact that there was a huge gap of almost 10 years between the SMR work and that of Krauss. So the SMR evolution may be viewed as a generalization of the integrated form of the Schrodinger equation. Remember, I had written down rho prime of, or rho at time t being equal to is the one obtained by unitary action on the initial state. And so this may be viewed as a generalization of the integrated form of the Schrodinger equation. A natural question to ask is, what is the generalization of the Schrodinger equation itself implied by SMR evolution? Under certain specific assumptions, this question was posed and answered in a paper by Gorini, Kosakovsky, and Sudarshan. This was a paper that appeared in 1976. The title of the paper was Completely Positive Dynamical Semigroups of N-level Quantum Systems. And independently by Lindblad in another paper which appeared in the same year, 1976, on the generators of quantum dynamical semigroups. This paper appeared in Communications in Mathematical Physics. And so in short, what one is doing is one has given the evolution, most general evolution of a most general map, or which takes a quantum system to a state, and this is the differential form of that evolution. It has the Schrodinger part plus some extra bits which allow for the possibility of accommodating or evolution of a pure state into a mixed state. And this was the structure given for the evolution that is under certain assumptions, which I won't go into, maybe in the question answer session. If there are questions on it, I will elaborate on it. And this structure can equivalently be written in this form. This was the form in which Lindblad had presented the work, and this equation is called the Gorini-Kosakovsky Sudarshan Lindblad master equation. So this equation then gives you a kind of a structure theorem, as I said, under certain assumptions, which go by the name of Markovian assumptions. They describe the evolution of an open quantum system and is an extension in that sense of Schrodinger evolution is Schrodinger evolution for a closed quantum system. Now, next I will spend some time on ECG and CPM. Please, the CPM here has some technical meaning which I will explain. Let me say that this has no political connotations. I'm not talking about ECG's connection with CPM in any political sense. Open quantum systems necessarily involve considering a system composed of two subsystems, the subsystem S and the system of interest, and the subsystem R, which is the rest of the reservoir. In quantum mechanics, the Hilbert space associated with a composite system A plus B is taken or postulated to be the tensor product of the respective Hilbert spaces. So what I'm now trying to do in the next couple of slides is to put the work of Sudarshan carried out in 71 and later followed up in 76 in a modern perspective. The tensor product structure of this Hilbert space describing composite systems brings in a new feature which is not present when you are not dealing with a composite system, and that feature is called entanglement. That is to say, the vectors in this tensor product Hilbert space can be divided into two categories: those which are separable, that is, those which can be written as a tensor product of a vector from the first Hilbert space and with a vector drawn from the second Hilbert space, and they are non-separable or entangled otherwise. This feature of quantum mechanics, which has no classical counterpart, occupies a privileged position in the field of quantum information theory, where one seeks to exploit such features of quantum mechanics to carry out tasks which are either difficult or impossible in the classical setting. So this feature, entanglement, has become a very important sort of tool or a resource for carrying out tasks which are classically impossible, and has been center of attraction in physics in the last 30 years or so. In this field, because of its very nature and objectives, one is required to spell out what are the most general operations that one can perform on a quantum system. So you ask the question, what is the most general state of a quantum system? What are the most general transformations that are permissible on a quantum system? Naturally, any such operation referred to as a quantum channel in this field must take a state to a state, that is, map positive operators to positive operators, preserving the trace. It turns out that all such positive maps can be divided into two categories: those which are called completely positive maps and those which are called not complete positive maps, but positive but not completely positive maps. So let me just explain in layman's term what this mathematically entails. In a finite dimensional Hilbert space, one can view these maps as positive maps are those which take D cross D positive matrices to another D cross D positive matrices. Completely positive maps are those which, even upon a trivial extension, continue to remain positive maps. Not completely positive maps are those where this extensions cease to have this property of being positivity. So in the modern modern setting, Sudarshan's 1961 work in the context of quantum evolution gives a complete characterization or a kind of a structure theorem for completely positive maps, a large class of maps which are relevant in this context. An example of a map that belongs to the second category, which is not covered by the CPM category and has played an important role in detecting entanglement, is the transpose map. So I've tried to now put the work by Sudarshan in 1961 in the context of uh, modern context by and it's, as you can see, plays a very important role, in quantum information theory. So the two papers of ECG cited earlier have been instrumental in initiating activity in a wide varieties of areas in physics and mathematics, open quantum systems, a mathematical question, positive maps, quantum Markov processes, definition of stochastic processes in the quantum domain, dynamical semigroups, and so on. In all of these areas, Sudarshan's work has played an important role. I must mention that there were certain precursors of these in the mathematics literature, but however, significance of Sudarshan's contribution and the foresight he had in raising and answering these questions is really indeed is quite remarkable, and I think it will continue to have an important impact in years to come. So thank you very much.